Now, as we have discussed the long chain structure of this glucose molecule, write it like this. We have CHO group over here. 1, 2, 3, 4, 5, and this is CH2OH, and third position we have H on the right hand side. Rest of the place we have OH over here, right? And on the opposite side we have what? If OH is there, then H will be over here. If OH is here, then H is here, so OH. And if OH is here, then H is there. So this is the simple structure of glucose molecule that we got after doing certain reaction, right? The exact placement of why this molecule or why this OH is on the right hand side, left hand side, we are not discussing those reactions. So this is the final Fischer projection, we can call it, we got of this molecule, and we call this molecule as what? The D positive glucose molecule. So you know that D stands for what? It is in the reference of glyceraldehyde molecule, and positive is because it is dextrorotatory, and glucose is the name of the molecule, and glyceraldehyde molecule look like this: OH, H, CH2, OH. So it is on the right hand side, we call them D, and if this OH on the left hand side, we call it what? The L structure. Now there is a certain reaction. We have proved that CHO group is there by reacting it with hydroxylamine, NH2OH group, right? And so the thing over here is that all the positive test of carbonyl group this doesn't give. This particular molecule doesn't give us 2,4 DNP test. What is 2,4 DNP test? DNP stands for dinitrophenyl hydrazine. That is a reactant. So I'll just draw that reactant over here. So we have this NH2 and H, then of course a benzene molecule over here. In this we have at position number, this is our carbon number 1, so this will be 2, 3, 4, right? At 2 and 4 position we have a nitro group over here. So this is known as what? 2,4 dinitro phenyl hydrazine. So that is the name of the species over here. These molecules also react with carbonyl group, but in this particular test this is not reacting. So means there is something fishy over here, means this cannot be the final structure. If it is, then this group should react or should give all the positive tests for the carbonyl group, but is not giving for this one. So what happens is, in general, whenever you have carbonyl group over here, for the shortcut I am explaining this H2 and go together, and carbon form double bond over here with this, right? That is how the final structure we get over there, and the final result we get after combining the carbonyl group with this amine group, we call that combine as what? The 2,4 dinitrophenyl hydrazone. This hydrazine become hydrazone in the product side. Okay, so this is actually not giving the hydrazone product over it. 2,4 DNP hydrazone, it is not giving that. It means CHO group, there is a very good possibility, is not in the free state as it was predicted earlier. Okay, so and it is a very important test over there. It is generally symbolized by, we get the product in the red orange form, yellow red orange form, we get the product, but in this case it is not giving this test. So that's why this theory need to be modified. Another version of it is that initially we have reacted one molecule of CHO, CH2OH 4 times, CH2OH, not CH2OH, simply CHOH, tetravalence, right? So 1, 2, 3, 4, 1, 2, 3, 4. One with the upper part, second with the lower part, one with OH and one with this part. So when we react this molecule with acetic anhydride, what are acetic anhydride? C double bond O, O, C double bond O, CH3. I am writing this like this, so just remember that this bond is with the carbon, it cannot be with hydrogen. So this is known as what? The acetic anhydride. So 1 mole of this molecule react with 5 moles of acetic anhydride and give us an acetate ion. So it gives us CHO, CHO, C double bond O, CH3 4 times, and over here CH2O, C double bond O, CH3. Now once we get this penta-acetate compound over here, it should still give positive test for CHO group. So now this group normally react with hydroxylamine, that is NH2OH, right? And give us the oxime. But once you form the penta-acetate, it is not giving the positive test for the hydroxylamine. The product will be called as oximes, but this reactant is hydroxylamine, NH2OH. Now it is not reacting with this compound. So what this reaction tells us is that after all the OH groups are engaged and form the acetate group over here, now CHO is not giving the positive test. It means there is a high possibility that CHO might be forming a ring structure with any one of the OH group. We will see that what is that OH group. It is basically this carbon OH group is engaged with this CHO, but we'll see that part like in a while now. But the point is that once all the OH group get engaged and form into acetate group, it is not giving positive test of NH2OH, which earlier it was giving, right? Normally it react with NH2OH and give us the oxime after reacting with CHO. But after forming this penta-acetate group, it is not reacting with NH2OH. Means CHO, there is a, like this concludes that this CHO is engaged with any one of the OH group and forming a cyclic compound. So that's why we come up with the new theory, with the new structure of it, right? Which explains like these anomaly also over here. So these things is also explained in the next structure. So that we will see now. So for the reasons just I explained, on the basis of that, we have to like modify our structure. So the modification, what happen is actually glucose form like in two forms. One is alpha form of the glucose and one is the beta form of the glucose. I'll tell you the main difference between them on the basis of structure, but for now, physically they are different because they have first of all different melting point. It has the melting point of 419 Kelvin and beta form has the melting point of 423 Kelvin. There is not so much difference in their melting point, but once you extract it by the process of crystallization, it crystallizes just above the room temperature. From the concentrated solution of glucose, it crystallizes at 303 Kelvin, just above the room temperature. And the beta form crystallizes again from the concentrated solution almost at the boiling point, around 371 Kelvin. So at 371 Kelvin, it crystallizes out the beta form, and alpha form crystallizes at the 303 Kelvin. Now what is this alpha and beta form? So glucose exists in two forms, alpha and beta form. So this form were also was also not accounted in this structure. According to this, we just have only one D, capital D, glucose structure. But over here, this capital D structure also exists in two forms, alpha and beta form. Okay, so I will now discuss that what this alpha and beta form. So we'll be deriving this structure from this structure only. So I'll turn on the sheet now. So what happened over here is, you must should know the basic reaction, that is whenever an aldehyde group interact with alcohol group, maybe of the same molecule or different molecule, we actually get acetals over here. If it is of same molecules, we get cyclic acetals. So this is what gonna happen over here. Now what happened in glucose molecule, I'll draw the old structure of glucose molecule. We have aldehyde group over here. I can write the aldehyde group like this, CHO group, right? We have carbon number 2. This is of course carbon number 1 because CHO is the high priority. Carbon number 3, carbon number 4, carbon number 5, and of course we have CH2OH. This is our carbon number 6. Okay, and in third carbon we have H on the right hand side. Then we have OH. If OH is this side, H, this should be OH. And carbon number 2 we have OH and H over here. Now what happened in this structure is this CHO, as we have discussed, is actually not completely in free form. So what is happening over here, this CHO group is interacting with the OH group of carbon number 5. Carbon number 5 is the last chiral carbon or the last asymmetric carbon, because all 4 groups to carbon number 5 is different. So there is an interaction between OH group and CHO group. And you should know this. If not, then I will just mention it now, that aldehyde group and alcohol group together, they actually form what, the acetal compound. They form acetals. So it is within the same molecule. So we'll get a cyclic structure over here. With there are two possibilities over here. But as I told you, there is alpha and beta form. So what we'll do over here is, I'll just draw this structure again. This lone pair will get transferred over here, right? So it will get what, complete negative charge. This OH, this H part will go over here now to this O, and via this oxygen carbon number 5 and the carbon of aldehyde will get connected. So structure, there are two possibilities over here of this structure. One I will draw in the upside and one I will draw on the bottom side. So the two possibilities are this CH and the OH on right hand side, right, of this, because it will get the H from this OH group from carbon number 5. So this OH might come on the right hand side or on the left hand side over here at carbon number 1. OH over here and H over here, and this carbon is connected via oxygen bond of the 5th carbon, right? So this connects to what? Carbon number 5. This is carbon number 1, carbon number 5, and bottom we have of course CH2OH, this carbon number 5. Okay, carbon number 1, we have carbon number 2, carbon number 3, carbon number 4, and this thing. Rest of the molecule 2, 3, 4 and 6, everything remains same. So we have OH, H, OH, carbon number 5 I have just explained, and this side we have H, OH, H. Now via this oxygen, carbon number 1 and carbon number 5 are connected. At carbon number 1 there are two possibilities. OH can be on the right hand side or OH can be on the left hand side. I'll just copy this structure again over. The rest of the molecule is exactly same. We have carbon number 1, carbon number 2, 3, 4, 5, and then we have what? CH2OH. This is connected via oxygen of carbon number 5, right? And carbon number 3 we have H on this side, OH on this side, OH, H, and H. So this is called as the beta form and this is known as what? The alpha form. So I will draw the cyclic structure of this now, right? I've just drawn like how this aldehyde group react with the OH group of the carbon number 5. So these compounds are nothing but the cyclic acetals. Cyclic acetals. Just remember one thing, this oxygen is connected via carbon number 1 and carbon number 5, right? So this will be our like main chain. So a hexagon structure we will be getting. It is similar to pyran molecule. A melting point of 417 Kelvin and it has the melting point of 423 Kelvin. Okay, and it crystallizes at 303 Kelvin, and this crystallizes this is like near to the room temperature, and this crystallizes at around 371 Kelvin. Okay, now I will draw the cyclic structure of it. Sorry, my bad. This has the melting point of 419 Kelvin. This has the melting point of 419 Kelvin. This has the melting point of 423. It crystallizes almost at room temperature, just above the room temperature, you can say 303 Kelvin, and this crystallizes at 417 Kelvin. Now let's go into the cyclic structure of it. So there is a molecule called pyran. It looked like this. And there is one oxygen. So this is pyran molecule. So see, this is nothing but a hexagon or heterocyclic molecule in which one of the vertex is oxygen. So this is what gonna happen over here. Just remember one more rule over here. So we'll be drawing this structure. First I'll draw the structure, then I'll tell you the trick of it. So we have like this structure. In one vertex we have oxygen. It can be any vertex. I have chosen this one because it is like little convenient, you'll just come to know. Now just remember, this oxygen is connected to carbon number 1 and carbon number 5. So this oxygen is connected to carbon number 1 as well as carbon number 5. Carbon number 5. Okay. And for the rest of the molecule, this will be carbon number 2, carbon number 3, carbon number 4, and CH2OH is not the part of the cyclic structure. So that I will be drawing. Now see, how do we draw? I'll start with carbon number 2. If OH is on the right hand side, first we draw the vertical lines over here. Right? We are drawing vertical lines for these groups over here. If it is on the right hand side, we draw it downward. If it is on the left hand side, we draw it upward. So at carbon number 2, OH is on the right hand side. So OH will come down, H will come up. Carbon number 3, H is on the right hand side. So H will come down, OH will come up. At carbon number 4, OH is on right hand side. So it should come down and H will come up. Carbon number is fixed. We always have CH2OH at the top, and in bottom we have 1, 2, 3. So one hydrogen is still there, right? This hydrogen is still there, which I forgot to draw. So this hydrogen is still there. So H over here. Now look what is happening in carbon number 1. OH is coming on the downside because it is on the right hand side, and this is coming on the upside. So this is known as what, the alpha form. When this OH and this CH2OH are on the opposite side, we call it alpha form. Okay. Now beta form, everything will be same except at carbon number 1, OH is on the left hand side, so it will go up, right? So I'll just copy this structure except carbon number 1. So I'll draw the structure like this. This is our oxygen connected to carbon number 1. Only at carbon number 1 there is an inversion of configuration. So we'll get OH on top, H on this thing, this CH2OH and this H. Now CH2OH of carbon number 5 and of carbon number 1 OH are on the same side. If they are on the same side, we call them beta form. Okay. Carbon number 2, 3, 4 is exactly same. You can like copy it from this structure also. Carbon number, this carbon number 1, 2, 3, 4 and carbon number 5 already I have already like drawn. This is our carbon number 6. This is our carbon number 6. And now see what is happening at carbon number 2. OH is on the right hand side, so it will come down. H left hand side, up 3. H is on right hand side, so it will come down. OH will come up. 4. OH is on the right hand side, it will come down, and this. So these are the cyclic structure. This is the final structure, and this is the most latest structure of glucose that we follow because it justify all of the reactions. You know, certain reaction it is giving, certain reaction it is not giving. So that actually gave us a very big hint that there's a very good possibility that CHO group is not in the free state. So CHO group is interacting with the OH group of carbon number 5, and CHO and OH interaction actually generally give us acetals. So this is the example of cyclic acetal because it was present in the same molecule. So this is the cyclic structure that we generally follow. And I'll write the full name of it. This is alpha. We also write capital D. We also write plus over here. Plus means because these molecules are dextrorotatory. So this is D, beta, and plus sign because they are still dextrorotatory. And then we can write glucose over here, right? This is glucose. Glucose alpha form and glucose beta form. So plus represent that the plane polarized light, when you pass through the sample of these molecules, they turn them what, in the clockwise direction. They are dextrorotatory. For that we have plus sign. Alpha and beta I've just explained on the basis of carbon number 1, right? And capital D means it is linked to what, the glyceraldehyde molecule. So this is the structure that we'll be following over here. Thank you.